And now we're going to start talking about atomic physics. And we're going to start by talking about Rutherford. And you should remember this from chemistry. We've got alpha particles. That gold foil. We found that most went straight through. 99.99% went straight through. And that means that the atom is mostly empty space. Okay? But a tiny, tiny fraction bounced back, meaning that there is a tiny, dense nucleus. And that's the next part of atomic theory was due to Niels Bohr. He studied atomic spectra. And it looks like this, okay? When you have a hot gas, the gas starts to glow, and it gives off these very specific bright lines of color when you look at it through a diffraction gradient. And you should have seen that in chemistry at some point. And each gas gives off its own set of colors, and they can be used to identify like different gases. When I take a cool gas and shine light through it, it absorbs those exact same colors. And they knew that when an electron drops down toward the nucleus, it's going to a lower energy, so it emits energy. But it looks like this. Here's the nucleus. We have the electron orbiting the nucleus. If it drops down, it's going to emit energy. And when an electron moves up, it's because it has absorbed energy. So if I have an electron here, and it starts to move up this way, it's because it had to absorb the energy coming in. If there was a little puzzle to this, okay? If an electron moved down just a little bit, it would just give off a little bit of energy. So maybe it would give off red. Okay? Then if it moved down a little bit more, okay, it's a little bit more energy. Maybe it would give off orange, okay, and yellow, and so on. So why were there only very specific colors? Why wasn't every color emitted? And what Bohr said was that the electrons can only exist in very specific energy levels. So you might have a hydrogen atom, and the hydrogen atom would have an energy level n equals 1. Energy level n equals 2, n equals 3, and so on. So when atoms move down energy levels, they jump between levels. Without ever being in between. So they move in a way we can't move. If I want to walk from here to the door, I have to be every point in between the two. Okay? But the electrons actually sort of teleport from one level to another. And there's a term for that. That's called a quantum leap. And if we want to find the energy emitted, subtract the energy of the final minus the energy of the initial energy level. And those are going to be on the reference table. Okay, and the reference table for that looks like this. Okay, so I can go for hydrogen, and it has the different energy levels over here, and their energies over here. The energies are in electron volts. And then they have one for mercury over here as well. So we have an example of that on the next page. An electron drops from the n equals 4 to the n equals 1 energy level, and we want to find the energy emitted. So if I go back to the reference table, I can find for n equals 4, the energy is n equals 4. Here, the energy is negative 0.85. EV for n equals 1, the energy is down here for negative 13.6 EV. Find the energy of the photon, I just subtract this. And negative signs are a little confusing, so I just do the bigger minus the little. So 13.6 minus 0.85 gives me a value of 12.75. Part 2. What was the wavelength of the light emitted? So we're going to use this equation to find the wavelength. But we're in the wrong units. Right now we're in EVs, and our constant H is in joules, so the energy needs to be in joules. So I need to convert this. And the conversion factor is 1 EV is equal to 1.6 times 10 minus 19 joules. So if I have EVs, for each EV I get 1.6 times 10 minus 19 joules. So if I want to do joules, I'm going to multiply by that number. So 12 EVs times 1.6 times 10 minus 19 joules per EV. These cancel and end up with a value of 2.04 times 10 minus 18 joules. Now we're going to take that and plug that into our energy wavelength equation. 2.04 times 10 to the minus 18 equals 6.63 times 10 to the minus 34th. C is 3 times 10 to the 8th, the speed of light, divided by lambda. And if I do my algebra correctly, I'll end up with a wavelength of 9.75 times 10 to the minus 8 meters. The third part of this problem is about as tricky as they can get. Can an energy of 9 times 10 to the minus 19 joules be emitted by an atom in the n equals 3 state? So first off, we got to convert that energy that's in joules to EVs. So it's 9 times 10 to the minus 19 joules. And this time I have to divide it by 1.6 times 10 to the minus 19 joules per EV. And our joules cancel, and we end up with a value of 5.625 EVs. Now, if we look at n equals 3, it has an energy of here 1.51 EVs, negative 1.51 EVs, negative 1.51 EVs. And if it's going to emit it, that means it's going to move down towards n equals 1. N, I'll write these values. N equals 2. It is negative 3.4 EVs. And n equals 1. 1 is negative 13.6. So the absolute values of numbers just get bigger as I go down. So if I take the energy at n equals 3 and change it by 5.625, let's see what we get. That gives me a value of 7.14 EVs. So that would be between these two. It would be someplace in here. And since the electron can't end up in between two energy levels, it has to end up at n equals 2 or n equals 1. It can't happen. So we've just been discussing the beginning of quantum mechanics. What does that mean? Okay, for very small things like electrons, the world is not continuous. Quantities come in small chunks, small pieces, like photons. Or small steps, like energy levels. And we've actually seen this before. Another example would be charge. Okay? Charges are always whole number multiples. Of one electron. Okay, I can have 1 electron, 2 electrons, 3 electrons per charge. I can't have 1.5 or any other fraction.